Okay, guys, let's go ahead and get started. I don't know if doesn't look like anyone's on, but this will be available for you guys after the fact. So last week we talked about the implementation of an actual extended Kalman filter in C++. We basically saw this as a basically an inheritance problem or a solution to this problem using inheritance. So we start with a basic filter, the idea of a filter. So a filter is basically a state estimate and a covariance estimate. And then we build on that idea of a filter base class that's basically composed of getters and setters for these two concepts. And then we extend that to an extended Kalman filter, which basically inherits the getters and setters for state and covariance. But then it also implements ways of actually using the extended Kalman filter algorithm, the mathematical algorithm, to compute a state estimate and a covariance estimate based on a measurement model and a state model, or a system model, or a process model, it's sometimes called. So today, I'm going to talk a little bit about what are the shortcomings of the extended Kalman filter model. Because if I didn't mention last week, I'll mention it now, that an extended Kalman filter is still, just mostly a linear filter strategy. So we use the nonlinear transformation to update our state estimate, but we linearize in order to update our covariance estimate, or our covariance is basically a fancy way of encoding uncertainty. So basically, how uncertain are we about the mean, or our guess of what the state is. Yeah, so that's enough. I think that at the risk of kind of confusing you, I'll stop there. Uncertainty is how confident are we that our guess for where the state is actually where the state is that we're trying to observe. So for example, if we're trying to estimate the position of our car, and we use an extended Kalman filter to update our position estimate, how sure are we that our guess is correct to where the car actually is in the world? Okay, so moving on. So now there's a lot of shortcomings to this approach, namely that a first order approximation to our uncertainty may not always capture all the uncertainty. So particularly in the case of a motion model, if we have a highly nonlinear like motion model, which the big model for modeling like vehicle or car dynamics, where you have front steering and fixed rear wheels, is what's called, the way of modeling this is called the bicycle model. And so bicycle model kinematics. I'll put this in the Slack channel. Okay, cool. So here looks like it has a couple of examples of dynamics for this. So I'll go ahead and just post the link to this paper in the Slack channel. Okay, bicycle model is a way to model car dynamics. Okay. So this is, you can see here from this paper that if we just restrict ourselves to the simple bicycle model, this is nonlinear, right? So cosine, it's nonlinear in the steering angle phi, because cosine is a nonlinear function. It's highly nonlinear. Like it has, if for those of you that are familiar with like a second course in calculus, you'd be aware of Taylor expansions and Taylor theorems, where basically you can represent a function to a desired level of accuracy at a certain point or about a certain point by taking what's called a Taylor expansion of the function. And so the Taylor expansion is basically a fancy way of basically representing your nonlinear function as a sum of polynomials. Well, a sum of your underlying variable or your underlying input to the function or your underlying argument raised to some power. So it'd be your underlying argument minus the point you want to expand about. So this is already a little unclear. So I'll go ahead for your Taylor's theorem. So I'll go ahead and just post the Wikipedia here. But the basic idea is you can represent a function at a point by expanding about another point, A, and you can say that if the real valued function is continuously differentiable, that is, you can take however many derivatives you want, then you can create very fine or very good approximations to the function at a point x nearby A by looking at the Taylor expansion, where you take the function value at the expansion point, then plus the derivative at the expansion point times a linear term, x minus A. And then you can do this to arbitrary order. So right here, this is a polynomial. This is like a second order Taylor polynomial, and also called a quadratic approximation. But the basic idea is when you linearize something like you do in the extended Kalman filter case, you are throwing away information, right? So you basically say your actual covariance will be, the covariance at your nearby point, which in this case, your nearby point is your previous guess for your covariance. Then you're going to update it with a Jacobian, which is the matrix analog of a first derivative of a single value function. You take a Jacobian and then you're going to times it by a difference vector. So the difference vector in this case will be your current state estimate minus your previous state estimate. So the idea is that you update your Kalman filter so regularly that you're always in a linear window where a linear approximation to the covariance will be valid. And that's just not true. So it's true with functions that don't change rapidly, like linear functions, for example. A linear approximation to a linear function is perfect because all of the information you need is encoded in the equation of a line. So before I continue, let me go ahead and copy this. And then we'll dive back into this. And for function representation using approximating polynomials. Okay, so back to this discussion for what this means for filtering. Well, if we have a linear process model and a linear measurement model, then we're fine. All we need is just a standard, I guess I'd call it like a linear or a vanilla Kalman filter. Remember from a couple sessions ago, I talked about the linear Kalman filter is basically just an optimal solution to the problem when you have a linear process model where your new state based on belief in your motion model is equal to some matrix or some linear operator applied to your previous state estimate plus some noise. And then the same thing for the measurement model. You have your actual so your actual state is some matrix times your your actual measurement is equal to some matrix times your state estimate plus some noise, or the true state plus some noise. And that noise is Gaussian distributed. So to reiterate, in the case of a linear process model and a linear measurement model, Gaussian noise, additive Gaussian noise applied to your state estimate to represent uncertainty in both your measurement model and your process model, the linear Kalman filter is optimal in the sense of it minimizes least squared. It minimizes the expected value of your least squared error, minimizes the expected value of your root mean squared error. So root mean squared error in this case is just how close to the actual true state is your state estimate. You look at the difference between what you guess and truth, and you square that term. That's the root, and then you take the square root of that. That's the root mean squared. Sorry, we've got a maintenance person here. I'm gonna go ahead and pause for a minute. All right, hold on for a second. You roll the trash bin. Yeah. The big one, yeah. Okay, sorry about that. I'm back now. All right, so now back to this idea of the linearization. So we now have, the linear Kalman filter is the optimal solution to the linear process model, linear measurement model, plus additive noise. Fine. So that hardly ever happens in real life. Like, you hardly ever have a linear process model and a linear measurement model. Usually you don't even have one, because if you have a line of sight sensor like a radar, you're typically getting measurements in polar coordinates. So you get a range and a bearing to a target, or in case of, yeah, I mean, usually measurements are not done in Cartesian coordinates. So you have to transform them. You're interested in a state estimate in Cartesian coordinates. So then you have to transform your measurement, or you have to transform your measurement to your state space and vice versa. And so the way that we accomplish that in the case of the extended Kalman filters, we linearize and we take a Jacobian, and that's how we transform a covariance estimate from basically from one state to the next. And that Jacobian basically represents a truncation of the Taylor series over all these terms. Okay, so there's a number of problems with this. For one thing, if your function varies quickly, that is your motion model or your measurement varies quickly, you may actually reach a point where linearization is not enough. Like, you underrepresent your uncertainty by taking only a first order approximation, and then you can get really bad filter performance. So what do I mean by that? Well, if you're only taking a first order correction for your covariance update, you may be neglecting to add some uncertainty due to the nonlinear terms in your Taylor expansion. And so if that happens and you you happen to, I don't want to say luck because it's not really luck, but if you happen to find a case where your uncertainty is underrepresented, your filter may actually diverge. Your estimate may actually be far enough away from the actual state of what what you're actually measuring that your estimate may become invalid. And you would see, an invalid Kalman filter estimate would be one that's very noisy or clearly diverges in the sense of there's wild fluctuation in your state estimate. And so one of the approaches to handling this this problem of uncertainty, basically underrepresenting uncertainty, is to do what's called unscented Kalman filter. So the unscented Kalman filter is basically, let me see if I can find a good view of this. And an unscented Kalman filter is just one way, but you can basically think of it as a clever way of basically being more conservative in how you transform both your state estimate and your covariance estimate. So let me go ahead and see if I can find a visualization of a Kalman filter, of an unscented Kalman filter. Visualization. So the unscented transform is the mathematical device that underpins the unscented Kalman filter, the unscented Kalman filter. So the idea is, God, this is such a terrible Wikipedia page. Oh my gosh. All right. Where's the picture? Oh, sorry, my apologies. This is so bad. But the basic idea is you're going to sample points around, your mean. So let's see if I can find one on Medium, because it really, you need to see a picture of this. Oh my gosh, that's the only one. Fuck. Yeah, all right. This will have to do. Okay, so the idea is that you're still assuming an underlying Gaussian distribution for the noise, but what you end up doing is you sample along the principal axes of your covariance ellipse. So you're still, in the sense of like a normal Kalman filter, you're still computing a mean. So like, the center of your probability density. And rather than basically just using a first order correction to propagate the covariance, what you do is you sample and you heuristically choose how far along the principal axes of this, and my apologies, this is a bad diagram because this is not at the center of the ellipse, but bear with me. This should be at the center of this ellipse. This original Gaussian covariances are ellipsoidal, meaning that they basically, in whatever Rn that they're embedded in, they are an ellipse. They basically, the shape that is encompassed by that covariance matrix would be an ellipse. And so the principal axes of that would be the major and the semi-major axes here. So these would be represented as eigenvectors of the covariance matrix, with magnitude defined by well, the size. I guess it would be the square root of the size of the covariance ellipse. So anyway, so what you do for an unscented transform is you take these points and you decide how you want to, how far from the mean you want to sample along these principal axes. So you could choose a point like here if you choose a smaller length, or you could sample a little farther out if you're more interested in behavior that's one sigma or 2 sigma away from your mean estimate. So if you believe that you want to be a little more conservative in your estimate and you want to see how points farther away from the mean estimate are affected, you would sample, outside of 1 sigma. If you're really just interested in more local behavior, you could just choose a smaller amount to sample. But in this case, you take the mean, you take these 1, 2, 3, 4 points that you're going to then pass through this G, this nonlinear function represents your motion model in the prediction stage, but then this also represents your measurement model during the measurement stage. And so what you do is you pass all 5 of those points through the nonlinear function, then you compute the best fitting Gaussian based on the output of these, based on the output that you got from passing those points through the nonlinear function. And so this is really neat because it's kind of, I always refer to, for better or worse, I refer to the unscented Kalman filter as a poor man's particle filter, because you're sampling multiple hypotheses around your best guess for what the uncertainty is. I mean, underlying it, you're assuming a multimodal probability distribution that there really is some best guess that most of your probability is focused around, and that the uncertainty around that is something that you would need to sample to kind of to ensure that you're properly accounting for uncertainty in the process and measurement models. And so, similarly to particle filters are sequential, what's called a sequential Monte Carlo method for estimation, because you're sampling from the underlying probability distribution. You're updating your hypotheses based on how well your sample, or how well each point in your sample matches the measurement that you get. And the unscented Kalman filter is a little different, but it's a similar idea of sampling. You are sampling about a representative distribution. So you believe that the underlying distribution is Gaussian. And so you're going to sample around that distribution and then transform these points. In this case, it ends up being, the number of points you have is 2 times the dimension of your process plus 1, where the plus 1 comes from the mean, 2 times L comes from, you have what is it? L, you would have L eigenvectors, and you would have L eigenvectors, 1, 2, because this is a 2-dimensional process, and then you want to go both in the positive direction and the negative direction. So that's the times 2. So you have 5 points, transform them, then you compute the approximate Gaussian that best represents the transform of this data. And then this now at the end of the prediction stage is what you use for your state estimate and your covariance estimate, where the mean now, you have some heuristic, some heuristically chosen weights that you want to use. You want to weight your mean highest, but you want to have a non-zero weight for all of your points around the mean. And this is basically a way of coming up with an approximate Gaussian that is more conservative and more adaptive to rapid changes, i.e. like nonlinear changes from your original or from the nonlinearity in either your process model or your measurement model. So I'm going to basically just take another 15 minutes and kind of walk you through the actual implementation. So here from last week, I introduced the Kalman, this header only Kalman library. I'm going to go back in and I'm going to look at include and then Kalman. Then I'm going to go back in here and I'm going to look at the unscented Kalman filter base to start with. One second, I'm going to grab water. Okay, so now an unscented Kalman filter base, this base class that we're looking at, well, it's a Kalman filter, right? So we should inherit from Kalman filter base. And we want it to utilize a system model and a measurement model. And so what are the things that make up a Kalman filter base class? Well, we need a state, because that's what we're actually updating. And then we also need a covariance from that, but we'll inherit that from base. We'll be able to use the base covariance. But like I was saying before, okay, so we're gonna basically template our system model type based on the state, the control, and the covariance that we've chosen. And these are all public, so so we want to be able to use these things in inherited classes, so they have total visibility to these. But then some things that we want to be protected, well, like I was saying before, the number of sigma points is going to be 2 times the dimension of the state plus 1, and we want this to be a static constant expression, because this will always be anybody who inherits from this will be bound by using this representation for the number of sigma point counts. And similarly, we're going to have a vector of type T and size sigma point count that represents the sigma weights that we're going to use. And then sigma points will be a matrix of type T that has this many rows and this many columns defined by the sigma point count. And so this matrix and this vector, they inherit from the Kalman. So they're defined within the Kalman namespace. I believe it's within types, but types comes in implicitly through the Kalman filter base. So now we're going to set up. We're going to use the base's state estimate, and then we're going to set up these protected elements. We have weights that we're going to use for the mean, and then we have weights that we're going to use for the covariance update. And now here, these are parameters for the unscented Kalman filter algorithm. So I would suggest you actually look up what each of these represent, but they are a way of encoding what I was talking about with this idea of how far you want to spread along the principal axes of the covariance matrix, how far you want to spread to sample from that. And then there's the other bit of how much do you want to weight those points. And that's encoded in these values. Okay, so then we have a constructor. We're gonna, pre-compute the weights, because these weights are static. So once you do this once, the weights are not updated in a probabilistic or a likelihood-based fashion. It's like I mentioned, it's heuristic. So that is one key difference between a particle filter and the unscented Kalman filter. But so yeah, so we do this up front. Then we have, well, we have a state prediction. So this compute sigma point transition, like I was saying before, S is a system model, and the system model incorporates G, basically. There's an S dot, I guess in this case, it would be S dot F, where we pass the state estimate and the control, and we get an output value representing the motion model applied to a state value. And so that's what this does. Then we return compute prediction from sigma point is what computes the weighted estimate of both the mean and the covariance. So that all happens right in here. Similarly, for the measurement prediction, we're going to do pretty much exactly the same thing, except instead of using the process model transformation, we're going to use the measurement model transformation, and we're going to use sigma measurement points, where sigma measurement points are the points that are sampled now in the measurement domain. Now, so it's important here that the manifold, oh, gosh darn it, I'm just going to say it. So the manifold that your measurement vector is embedded in, that may not be the same. That may not be the same embedding manifold or the same dimensional space. In the case of like Rn, it may not be the same dimensional space as your state space, right? You could have a 3-dimensional state space and only measure a range and a bearing to some landmark, and then your measurement space is 2-dimensional. So now you have this. Basically, the compute prediction from sigma points that you apply to the state, you apply that to the sigma state points, where now these sigma state points will be, you'll have 2 times L, which in this case, if your state dimension is 3, you'll have 2 times 3 plus 1 is 7 columns, and you'll have 3 rows, making that a 3x7 matrix that represents your sigma state points. Where for the sigma measurement points, if you're only able to measure 2, you'll have 2 times L plus 1, that's 5 columns, plus or times 2 rows per column. So then you'd have a 2x5 matrix representing your sigma measurement points. So I hope this is clear. Ask in Slack if it's not. Okay, so the main point I'm trying to get across here is that we're using the same templated logic here, and this is a great point for reusable code. See here where we pass a templating argument for what we're going to be computing the prediction over, like what underlying vector are we going to use? Well, I guess in this case is what underlying class are we going to be computing our prediction over? And so here you can see it's the same function, different templating parameter and different input, but we only have to write this function once, which I really think is a really awesome thing of C++. And you know, probably the hardliners among you who for Python could probably say, well, yeah, I can do that a lot easier in Python. But here's the catch: you don't get type safety. You don't get type safety in Python without writing a boatload of exceptions and having to handle nearly any input that a bad user is going to throw at you. But with C++ and implementing templating, I get reusable code that's type safe. So C++ wins. So anyway, like I was saying, we compute the weights, and we use that based on these member parameters, lambda and gamma, and then we compute these weights. You can see here that this first point. So the way that these matrices are laid out is the first column represents the mean. Then we'll do the transformation and we'll get the next 3 points would be the positive, going in the positive direction along the eigenvectors of the covariance matrix. So yeah, so the eigenvectors, principal axes, same deal. And then the remaining columns of the matrix, so the remaining L columns would be the along the negative side, I believe. In any event, we're going to apply this weight to the covariance, or to the estimate based on the transformation of the mean. So we're going to weight the mean more heavily. So this will be a value that is greater than these WI. So the important point I guess I want to make here is that all of the points that you sample around the mean are weighted equally, and the point in the middle is weighted more. Certainly you could change this paradigm if you really wanted to, but I would advise against it highly, because remember, your mean estimate is still what you believe is the best guess. So any update you have based on a motion model or a measurement model should take into account or weight the mean estimate most in that final hypothesis. Okay, so the sigma point transition, like I was saying, we're going to apply S dot F, which this is the system model, and we're going to transform all of these points. One second.
So you said.
It's buried. So let me actually give me a second. Go ahead. Come on. Dora. Okay. Come on. It was up here. Okay, so I'm going to go ahead and wrap up for this week because I have someone here, but we'll pick up from this next week.